So, we continue from where we have stopped or a little bit earlier. I was just talking about electrical supply or electrical services in construction site, but I think I was just looking before that to other thing we have looked into and site, but I just want to tell you about circuit breaker again and then we will look into the site. So, as we discussed in the last class, we said this is a magnetic core, this is a magnetic core and live comes like this, coils around and then goes to the load, and then neutral coils on the secondary side and then goes to the load. So, when there is same power, current is same in the live and the neutral, that is there is no there is no short circuit or anything of that kind, right. In that case, this neutral current which is opposite direction, because it is a kind of return current and this is the current going. So, what will happen is this will balance each other. So, there will be no magnetic field generated, because this current direction is like this, and if you see the neutral, it goes like this direction, and neutral opposing current, right. So, its direction is like this. So, neutral current will be opposing current, because neutral current will be return current. So, return current direction is something like this, opposing direction. So, they are opposing each other as a result. So, this is the live current, right, goes like this and then follows through the load, and neutral current comes like this, and they are opposite direction current and they are same. In that case, in the core no magnetic field will be generated, there will be no magnetic field, because there is a current in the primary and just exactly opposite same amount of opposing current coming into the secondary. So, there will be no current generated, but in case there is a short circuit or something and excess current passes through this, there is a difference between these two, then this there will be magnetic field generated in the core, magnetic circuit will be complete and it will actually activate this this solenoid system, because if with no magnetic field here, no current would have passed through this, but with magnetic field the current will pass through this and it will activate this solenoid circuit breaker, which will break the circuit, and this is a switch to test the same. So, this is what I repeat, and then we go to the scenario of the site, construction site. In construction site, normally you will have obviously there will be main distribution, this is the substation, then from there the main distribution unit, there will be some crane or similar sort of thing, there will be some movable plant, and this electromagnetic basically electromechanical units, lot of them, and then hand tool service, lighting system, etc. Then some distribution unit for this, and this might be going to the hand tool sections and so on. So, in the site also similar, but then you will have lot of mobile equipments, mechanical cranes and so on. So, that is, but basic principle is similar. So, coming back to this, we just looked into the performance of this one, last class we are looking at, and obviously the response of this circuit breakers are much better than cartridges or fuses that were used earlier. So, that we explained yesterday. Now, I think then we are talking about transmission through high voltage, and then AC is economical, etc., and load must be balanced. This is what I think we are mentioning, that in the 3 phases load must be balanced. Now, there are 2 types of load, as I said, resistive, where power is consumed as heat or light or work is done, and there is reactive, coil, capacitor, etc. I think that is where we stopped yesterday, coil, capacitor, etc., where power is not consumed by conversion to heat or light, but it is simply stored and released in alternating, when you have alternating current. So, we would like to but the voltage, RMS voltage is given as RMS current into what we call Z impedance, right, and V I is V I is what is voltage and current. This is not the power, but V I cos theta, or cos theta represents, or some what we call power factor, represents the proportion of resistive load compared to the total load. Now, what it is actually, let us look at it a little bit more, little bit more. It is something like this. You see, since there is a phase difference, the peak of the current in a resistor, if I apply an alternating voltage, peak of the current in a resistor and peak of the current in the capacitor, they will not be same time, they will not be same time, because one can derive this, but I am not interested. You must be remembering Q, the charge, is equals to capacitance into V, right. Q, the charge is proportional to voltage you applied against a capacitor plate, or small q, whatever I write it, q, small q, let us say, and dq dt is equals to the current. So, if you have an alternating current, rate of change of charges is equals to C dV dt. Therefore, in case of so this is I. So, I is not proportional to V, rather rate of change of potential, rate of change of potential. So, if it is V is equals to, let us say, V sin theta, V 0 sin theta, dV dt will be V 0 cos theta, right. dV dt will be V 0 cos theta, whatever sign it is, right. So, essentially I is if it was proportional to V, if it was proportional to V, that is the case of resistance, because V is equals to IR, that we know. Here it is the resistance or equivalent resistance you can calculate out based on capacitor's value, capacitance value and all that, but you can see that it is not in phase with the I, because this is V 0 sin theta. In case of resistance, this will be V 0 sin theta, this will be also I 0 sin theta, current will be So, this sin theta and cos theta is out of phase by 90 degree. When sin theta is 0, cos theta corresponds to pi by 2. So, therefore, there is a phase difference of, in fact, current leads by pi by 2. Similarly, in a conductor, I mean in an inductor actually. So, this is what it is. So, one can show that they are not in phase, and in a complex plane, if you draw it complex Cartesian plane, this is the real axis, this is imaginary axis, right, imaginary axis, this is negative imaginary, positive imaginary. So, there will be one component here, resistance component, capacitance equivalent, which is equivalent what we call reactance, right. So, it is given as 1 by twice pi f c, reactance x of the capacitance will be given by twice pi f c. So, that is they are out of phase by 90 degree. So, as a result, if I combine this together, I can just write like R plus x. What we do is we have impedance Z equals to R plus x square. And in case of inductor, V is equals to L di dt. The EMF generated or voltage generated is proportional to rate of change of current in a coil. So, in case of a coil, the back EMF generated is proportional to rate of change of current. So, this is inductance, and therefore, again you can see that they will be also out of phase, because this time current will be I, if it was I sin theta, it would be I cos theta, where voltage is in sin theta. So, it only the I now leads by, lags by 90 degree, I lags by 90 degree. So, therefore, its reactance twice pi f l, reactance is x l is twice pi f l, So, reactances of inductor and capacitors, they oppose each other. Reactance of capacitor and inductors oppose each other. The current in the inductor lags by 90 degree, while that in capacitor leads by 90 degree. That is right. So, total impedance is given as Z square R square X C or X C X L square, because they are 90 degree out of phase. So, 100 so I mean one is lags, they are 180 degree out of phase. So, just negative sign would do. So, R square X C square minus X L square, all right, and Z square is equals to. So, this is impedance. So, impedance is square root of resistance square plus the reactance, combined reactance of capacitance and inductor. Now, the power loss only occurs in this, and R by Z is what we call power factor. R by Z is what we call power factor. R by Z is what we call power factor, right. So, R by Z is what we call power factor. The proportion, now higher this value, if it is a purely resistance, then pure resistive circuit, in that case this will be equals to 1. Purely resistive circuits, this value will be equals to 1. Now, the voltage required is I Z actually, voltage required is I Z. So, you can see that the V is equals to I Z in an alternating current system. So, if my Z value is high, my voltage will be high for the same current scenario, but then I will be utilizing only a fraction of it. The fraction is given by this power factor. Therefore, I would like to maximize this power factor, or do not like to have lower power factor. If I have lower power factor, which means that unnecessary wastage, unnecessary, my V required will be higher. So, one of the principle is that the power generated is transmitted high voltage, that we have said, and then we have said that there are two types of load: resistive power is consumed as heat or light, reactive in a coil, right, capacitor etc., power is not consumed by conversion into heat and light. And we like to, the above two gives impedance Z, and all are of course connected parallel. The system is more efficient when resistive load is more compared to reactive load, right. So, power factor is resistive load divided by total load, and we like to keep it at high value. We like to keep it at high value. We like to keep it at high value, right. So, power factor should be as high as possible. Ideally, or in houses, or usually in houses, it should 0.8 is preferred. Power factor of 0.8 or above is preferred. The reactive load comes from inductors and capacitors, as I said, and I have already said that reactance of an inductor is twice pi f L, where f is the frequency, L is inductance of an inductor. So, when you have coils like magnetic field and like such for example, I gave an example of a choke. The motors will have coil winding, and there is a reactive component there as well. So, you might likely to have, where you have industrial situations you can have, or buildings you can have where lifts and similar other devices are working, there you might have a lot of inductive load, So, we would like to really change in current which produces back EMF. So, in case of inductance is high, power factor correction is required. So, we would like to have a power factor of 0.8 or above, possibly 0.9 or so. So, where you have lot of motors and similar sort of thing, where there are coils, magnetic field is generated, you are likely to have lot of inductive load. So, we would like to correct this, power factor correction should be desirable, right. Usually in loads, the loads that you come across, capacitance is less. If the capacitance is also high and inductance is also high, inductive load is reactance from inductors and capacitors both are high, they would have cancelled each other. But usually capacitive load is less. It is usually from inductive load, because motor etc., most of them will have inductive load. So, to maximize this resistive load, you use sometime power factor correction, right, using a capacitor. So, important issue is, first is, okay, this issue I will come to that. So, I might actually, a power factor corrector might be used in a, for example, there are a lot of labs in the main building, and let us say I have power factor is going somewhere around 0.6 or 0.7, lot of motorized equipment and such things. Then what I would do in the main substation, I would like to put a capacitive load in parallel, or accordingly, appropriately, so that finally I get the inductive load is, reactance is cancelled out by capacitance, because I said that the Z square is equals to R square plus Xc minus XL square. So, because they are 180 degree out of phase, so they oppose each other. So, therefore, I would like to correction, power factor corrections are, the devices used for power factor corrections are capacitors. So, appropriate design of the capacitor, size etc., I mean the capacitance on. So, this will be done to correct the power factor correction. The other issue is of course related to other issue is related to what? Other issue is related to balancing the load, right, balancing the load. Now, when do you do balancing the load? Because in a multi-story building, as I said, you might have something like, let us say, 35-story building, 35-story. So, what will you do? Such kind of, the electric load is pretty high. So, a single phase supply will not do. Single phase supply goes to the room, because our appliances are mostly single phase, live neutral, 2-wire and 3-wire with the earth-wire connections, many appliances. So, in a building of the kind of 35-story or something of that kind, you will have lifts, might have number of pumps for firefighting requirement and so on. So, there will be some centralized 3-phase motors or 3-phase equipments. In addition to that, you will have supply to the various rooms, which are single phase supply. So, as I said, the three phases, the load must mean that each phase should be more or less similar. Load, for example, this is L1, L2 and L3, and all the cases you will have a neutral, because single phase is through the neutral, this is also through the neutral. Neutral point must be common somewhere there must be a neutral. So, live and neutral for the first one. Now, the load in this one and load in this one and load in this one must be same, otherwise it creates disbalances in the back, like at back stages, where from generations and so on. So, it creates problem. All the 3 phases might be loaded almost similarly, right. So, that is what is a requirement from the electrical energy generation or everything point, those point of view. So, how do I do it? 35-story I divide by 3, I get 11 point something 6 or something. So, what I do? I make it 12 and 11. So, that is how I distribute. If it is an area wise, 1/3 of the area will be similar, like common motors etc., that obviously will go directly from 3-phase supply. But after stepping down and then single phase supply that I am taking, that would go actually equal area wise. As I was giving an example, supposing you have like number of blocks, number of bays in the building, right. So, long building, academic building, let us say of the kind of IIT Delhi, very long building, there are what do you call bays sort of. So, you try to put equal number. If it is a building of the kind of a classrooms. So, put similar size classroom, divide them into 3 similar sized one and connect it to each phase. like that, you know. So, try to see that equal area is supplied from each phase is, so area supplied from a phase is same as any other phase. So, that is the other issue, that is the other issue. So, phases must be balanced, power factor correction is required, and earthing is required to avoid the injury to person. So, these are the three things one is to take care of, irrespective of, you know, irrespective of whether you are a civil engineer or electrical engineer, this knowledge must be available to you. That okay, we should have high power factor correction, I mean power factor. If required, apply a correction, that means put a capacitor, and then load must be balanced. So, planning stage itself, and load center substation location should be, usually you see its dimensions etc. are given in the National Building Code. What is the dimension required, because it will depend upon the functional requirement of the substation, machine sizes and all that. Some ideas are given in the National Building Code, gives you some of the guidelines related to this. Where it should be located? It should be located at the load center. For example, if you know the load, maximum load is an area 1, there is an area A2 and area 3. Now, the load in A, you know, it should be weighted average, the distance multiplied by the load, distance multiplied by the load from the load center substation, from the substation, distance multiplied by the load, that has to be minimized, that has to be minimized. So, your location x, y, z, you can actually, it can be a simple problem. If you divide in your area into coordinate system x and y, right. So, distances are x is the, let us say x is the substation location, xi is the location of ith load center loads, and similarly yi. Sum total of this square, this should be minimized, because the distance is given by square of x minus xi. In Cartesian coordinate system, you can, you know, locate coordinate centroid point of each one of them, of the load in a building and in a room centroid. You can, you know, even take Euclidean distances as we call it, and as an approximation, and load multiplied by the distance must be minimized. So, sum total of load multiplied by the distance must be minimized. So, this is the distance multiplied by the load ai. So, if I say so, it could be something like this. Let us say for area I, ai, and the distance from x minus xi square and under root of, you know, under root of that plus y minus yi square. Sum total of all this ai multiplied by this should be minimized. So, minimize let us say minimize sum total of ai, you know, Cartesian coordinate like Euclidean distances we will call. That will give you the least cable requirement, cable cost, because the cable size will depend upon the amount of load. So, amount of load. So, if you minimize that, that means cable sizing, unless of course they are all similar, then there is no problem, you can just put it at the center as or what is available at the site, So, substation should be located at the load center of the centroid of the whole area what you are dealing with, right. But then in multi-story building, it is usually has to be at the ground floor level above HFL. Those requirements are, safety requirements are there, you do not put it somewhere up. So, above HFL, away from, you know, it will also be a fire separation has to be seen. So, those issues comes in, and therefore, the location comes in. But in a spreaded area, it should be in the load center, you know. So, that is it. Okay. That is what I have already said. Distribution box must have fuse or MCBs followed by switch. Fuses, and that is we have said, should be at the load center, substation, location of substation at the load center, at ground floor to reduce conductors, direct access to it for installation, because if transformer has to be taken out and placed, right, transformer has to be taken out and placed, or maintenance has to be done, you have to lift it, put it on a truck. So, transport direct, this should be available. Must be placed above highest flood level, preferably location in a separate building close to, if there is a generator room, close to generator room. So, this is what it is, all right. You can see that actually. You can see in the campus, in this campus, for example, civil engineering substation is accessible from the road straight away between block 4 and block 5, you know, it's accessible. There is an entry there, there is an entry available there. I mean, they have made some cycle stand, but I suppose although vehicle cannot enter, but there's a, and it's just almost isolated in the between the two blocks in the ground floor level itself. So there's some access available, not for really truck or something, but changing of transformer, there should be actually, this should be, you know, the truck should be able to go and come. Okay. So that's what it is. Right. So transformer, usually we might have to take some time decision related to transformer. Obviously VI capacity is one thing that you know, how much kVA, kilovolt ampere sizing it has to be, that is known to you, that would be known because of what you are dealing with. And generally, you know, eddy current reduction is done because you will have core, you can see that there will be core is separated by sort of insulator to minimize the eddy current losses, right. And cooling is done either by oil or air cooled system. Currently it is air cooled one which are efficient. So oil cooled systems are not above, you know, they are not housed above ground floor. Air cooled system are more efficient, and oil cooled there can be fire hazard and all those kind of things. So they are not actually preferred. So that's this kind of guidelines, safety guidelines are there. You want to calculate out how much is a load at the planning stage. So rough guidelines are given in National Building Code. Normal lighting, take 20 watt per meter square, 20 watt per meter square. Normal lighting, take 20 watt per meter square. So for example, if you know the area of your floor or total building, for lighting only this much, how much you would need, it will be required. If lift pumps are there, then it would be more, and if AC is there, additionally 11 watt per meter square you got to take. So these are again the values are given in National Building Code. To start with, how much is the capacity you need for a given building, roughly you can estimate it out. So you know, like before even giving, so one has to look into those kind of things. I have already told you sizing of electrical cables, this can be done, this can be done using diversity factor. I mean, first you will first like to find out, let us say I have 10 lamps, right, 10 lamps and each 5 ampere rating, and then maybe some sockets. So you know, another 15 sockets, you know, 5 ampere rating, and I want to size the cable connecting to all of them. Then I use the diversity factor concept which we have talked about, right. So sizing of these cables, and then size for how many amperes. So the factor, diversity factor multiplied by 5 into 10 plus, you know, say 5 into, if there are 15 number of sockets, something like this. So multiplied by, that would be the, that many number of, that's for that much ampere, you know, you have to design the cable. And as I told you the other day that you know, the current rating related to, because R is equals to rho L over A, rho L over A. So for 1 meter length, you know, sizing you can just determine, right. Okay. So the current rating you can, you know, based on resistance is this. So if you know the current for 220 volts, for current rating, what is the area or mass or dimension size of the cable, that you can find out. So this can be found out, or you can look from some tables. That's very simple, it's not very complex anyway. So this is what it is, right. Then you have to provide details of earthing and lighting protection. Guidelines are given in lightening protection, not lighting, lightning protection. These are given, guidelines are given in National Building Code, like how many number of, you know, because in case of lightning, the high voltage that is generated in the cloud, this can hit the building, but it must straightaway pass through the ground. So therefore you provide conductor at the top of the building, and these guidelines are given in National Building Code. So this lightning protection, this is given in the National Building Code. So, this is about all about electrical services system. This is all about electrical services.